Today we have Satya Ramachandran joining us. Satya, brief intro. He's a VP at Neustar and is responsible for the marketing analytics platform there. He's got more than 20 years of knowledge and experience in distributed computing and real-time analytics. So with that, Satya, we'll be talking about predictive models. Take it away.
Thank you. Thank you. I want to apologize for this title. It looks very fancy, but they wouldn't let me in if I don't have a fancy title. So, but anyway, I think the thing is we've been building a decision support system for quite some time, and this is like a few aspects. I wanted to just talk about a few aspects that we put into our workflow. And again, I wanted this to be an interactive. By no means are we the best. We have obviously had a hypothesis as we built the system. So hopefully, I'm able to present that, and then we have a dialogue. And at the end of this talk, we kind of get to some place where both of us are smarter. Hard to follow Sumit's because this looks less fancy, because it's all about the AI and machine learning. But this is kind of an engineer's view of how to look at the analytics lifecycle, right? You have at the top, first data gets processed, and there is an ETL workflow. You first make sure it is ready for modeling. Then you extract features out of it. It's called feature engineering. Then you build the model. You score the model, and then once the models are scored, you do predictions, and the cycle continues, right? You keep iterating on the model. This is, even though it's like there are 5 stages, it's pretty intricate. Each step has a lot of details that we need to cover. So I'm going to focus on 2 areas. The first area I want to focus on is scenario analysis and reporting. This is something that doesn't get covered that much, even in this hype of AI and machine learning, in my opinion. And I feel that decision support systems is one reason why I got into this field, is not covered as much, right? And I'll kind of demonstrate it with it's not a demo, but just kind of show you what that means. So on this chart, if you look at it, there is what this chart is it maps out what the offline conversions are over a period of time, right? Starting from December 4th to mid of February. The one on the blue line was all the historical stuff. This already happened, so you can't influence it. But then the dotted lines are the future. So this is the prediction. And there are 2 types of lines. One is what would happen if you didn't change anything, right? Kind of saying, okay, this is how your offline conversions would be. And then the other line, which I know it's kind of short, but the other line is showing that if you do certain actions, you might have potentially a lot more opportunities, right? And this is the whole predictive aspect of analytics. And that's well known. And with that, and in here, how do I influence it? How do I influence the opportunities? You look at it, and in this case, this is the audience segments, right? These are audience segments. The question is, these are and then you see those numbers. Those are the spend on audience segments. Remember, you're doing an advertising campaign and you're targeting all these audiences. So clearly, it's saying that you need to increase. If you increase your spend on certain audience segments, right? Clearly, this is coming from a real data because you see a not applicable. That only happens in real data. But so you increase your spend on certain audience segments, young and free, function-driven, tech enthusiasts, and you decrease it on certain audience segments, business first, no frills, dreamers, hard to convince, you can get to your predicted outcome. Now, this is great. A machine has run a model. It's done this prediction. Clearly, as a marketing person, like you don't want to accept it as is, because my boss, the dreamer segment was, my boss came up with it. I cannot go against him. I cannot just go ahead and decrease it. And this is where a decision support system starts coming into play. What happens is you're able to actually go and make those changes real time, and then you're able to influence those outcomes. Now, from that demo, I just wanted to simplify what happens behind the screens, right? How does these things actually happen? So first thing is, this is a very simple representation of the data behind. So you have some data, which is, you have time, product, region, you have number of impressions, spend, and the Google query volume, right? The number of impressions is the number of impressions people see. The spend is what you spend on the advertising, and as a result of it, the Google query volume is the number of searches that you get. And so this is a dimensional model. It's fairly well understood by people, and there's a lot of course, with big data, it's become even more. There's a lot of knowledge, and there's a lot of experience in this area, right? And you can get quite a lot of insights. But like what we saw in the demo, if you really wanted to then go and like say, okay, fine, what if I want to change it, right? What if I wanted to? I had this kind of a spend. What if I wanted to increase my spend? And then can I see what the impact would be on my outcome next? You could always like replicate the spend, and then you can increase it by 10%, and you can come up with the total spend. That's easy calculation. The question is, how do I know what the resulting Google query volume is going to be? That is in my opinion, that is what analytics kind of makes it possible, right? First, you're able to say what is the predicted outcome, which is predictive analytics in the sense that you're able to predict what the future outcome would be. But more importantly, the decision support and management, and I know that this is not talked about a lot in AI and machine learning, is how do we influence that outcome that machines are predicting, right? How do you interact with the system, and how do you provide your own inputs and influence the outcome for the future, right? And I call that decision support and management. I really think that this, and once this matures, is what is going to get analytics into mainstream business. How does that happen? First, same data. To build the data, you need to flatten out the data, right? You need to create a matrix, because most of the modeling algorithms work on flat data. They don't work on normalized data. So you need to flatten it out. Then you need to group them into sets called features. In this case, there are two features. The first feature is TV product impressions, which is the number of impressions on TV. The second one is TV local spend, right? These are the two features, and clearly there are typically hundreds and sometimes thousands of features that is present in the data. Once you create these features, then you assemble them into an equation, right? And your outcome is on the left-hand side, right? And then all of those features which influence the outcome are on the right-hand side. And then you have your the C1 and C2 are coefficients of that equation. And modeling is nothing but you're estimating the coefficients of that equation, right? And once you estimate the coefficients of that equation, then you put it into a matrix form, and then all of the calculations would be matrix multiplications using this model in the matrix form and the input in the matrix form. And let me take the same example and tell you how it works. Previous example, we are able to calculate the increased spend, and then We then get the coefficients for each one of those features, and then we then multiply the model in the coefficient form with the input, and we get the final form here that would tell you what is the predicted outcome. And the one you see on the blue is the predicted Google query volume. You take that back into your input, you aggregate it, and then you will get the final predicted form for the Google query volume if you increase the spend by 10%. What is the problem? And this seems fine. The problem is this is how a typical schema looks like. You have tens of dimensions. You have a large number of rows, right? We saw like 15 rows there. You have like tens and millions of rows. And you have to run these calculations across all of these dimensions and across all of these rows, right? And that seems to be, and that was especially difficult, right? So we've done reasonably well. It's taken us a while to go from like really, really slow calculations to right now we're able to do these calculations really fast in seconds. And what I'll be talking about in the next couple of slides is what did we do at a very high level, and then I'll probably take questions. So first, it was very simple, and this is what people do. They write a SAS, like you write a SAS macro for the calculation. You have it in an Excel table, and then you run this. And the number that you see, the 1,200, are not the features, but it's the number of variables that you can influence, right? The number of rows which you can change. So we had like 1,000, like a small 1K rows. It would take us, I should have the thing in there, but it would take us minute, 2 minutes, sometimes 3 minutes to run these calculations. Then we took that, and then we just put it on a bigger computer on the cloud, and we ran the same calculation, nothing else. Same calculation, just use simple, the same SAS stuff, but running on a cloud on a bigger machine. We were able to support a large number of variables, and while this was in minutes, this was like less than a minute or something like that. But that was not enough, because the number of decision variables, or the number of variables that our analysts or our end users wanted to change started increasing quite a bit. And so the next step, we had to do some computer science to make sure that it scales there. And I think the last one is what I thought was the biggest innovation we did in this space. And let me go there. So the first set of things that we did were just computer science. So first you saw the matrix. We materialized the matrix. We just materialized the matrix. We kept it there, and we used various techniques to make sure when a user changes the value gets reflected in the matrix as soon as possible, right? So just being able to cache always the input that the model requires. If there is any change that happens, we would log the data, and then we will take the logs, and then we'll apply the logs on the matrix. We'll then also optimize how this matrix is formed, and when there are changes in the matrix, how it gets written on the disk. That got us from minutes to tens of seconds in there. But it did not help us, because with these changes, we were able to run these kind of models only at one level. We were not able to run different kinds of models at different levels. What that means is we were able to run it at let's say you had zip code, state, and country, Suppose you made changes in your zip code, and you wanted to say, okay, fine, if I increase my spend on a zip code, then what would be my outcome? We were able to do it, but let's say you wanted to now like apply the whole thing across the entire state, or you wanted to apply it across all the country, and then you wanted to run a model. These changes alone did not help us. The next one, and this is something that I thought was unique with what we did with MarketShare, is we then went and married the dimensional model with all the dimensions and the fact. We married the dimensional model with the math itself. So one you see on the left-hand side is your dimensional model with all your dimensions and facts and so on and so forth. The one you see on the right is your model, how the model is represented as an object. We married these two. So at any point of time, let's say you're going and making a change. Let's say you're making a change at the country level, and you're just changing, you're making a global change. Instead of running a model, you're taking all of that data, running a model at a zip code level, you would run the model right at the country level itself, right? And all of this is happening at runtime. You're not like creating the model, you're not running the model, all of this is running at a model. This, I believe, is like an important aspect of creating any large-scale decision support system, right? So I'll stop right there. This is one of the things that we worked on. Any questions? Any thoughts? How many of you guys are actually running like predictions and decision support systems like this? Okay, what's your experience in? What's your opinion?
It's kind of interesting because I actually had similar experience from my previous job. It's not currently. Currently is a little bit different, but it's where we build some dynamic systems. So it's not only model, it's users that can interact with models. And based on user interaction, we changed how model actually works with users. So like in 2 words, we built recommender system that recommends you some. It was book recommender actually, sum up. But some people like or dislike different sets of books or categories. So they interact with that system. So you may like or dislike. So then, and it goes like by decision tree, maybe similar like you had. So then you dislike it, then it shows you like similar things. Like if you dislike that book, yes, according to trees, people like you maybe like that category, but you already didn't like that category. So they show you like next category. So anyway, we built something similar. This topic was interesting for me, and at least from that perspective. So that's my experience.
Awesome. Okay, we had a couple of folks. Any other thoughts on what you guys did and how is it similar, different? So I mean, and again, we were able to scale. We were able to scale to a large number of these sort of scenarios, and this is our biggest was the reason why we were able to scale. The second thing that I want to focus on is feature engineering, and this is hopefully this is a topic that a lot of people are exposed to. Again, how many people here are familiar with feature engineering, or you guys are already doing that? Okay, that's 5, 6 of you. We talked about it when in the introduction. It's grouping the data into set of elements called features. Features are nothing but numbers with this is a recovering data person who's kind of talking about modeling. Numbers with associated context with it, right? You have sales for a region that becomes a feature, so on. Just to explain that further, so here you have this is data, impression data, and activity data, and then finally conversion data, right? And then you're getting it on a per user basis. So So the first one, the striped blue line, is TV impression data. Then you have search impression, print, and that the one is like, you've taken that. The user has put it in the his shopping cart, visited online, and put the object in the shopping cart. And then, of course, you're trying to go and predict how many such actions would the user do, and you're measuring that, right? And the feature that you are trying to come up with here is generalized hazard transform. Again, the feature itself is not important, but it measures the decay of an impression, what effect it has on an individual when it comes to purchase. That's what it means. Not important for our talk. And what that translates to is you measure the amount of time each one of those impressions, the lag or the time it takes from each one of those impressions to the effect, and you take the minimum time and you put it in this formula. Okay, so here we are only interested in TV impressions, so we filter out all the TV impressions. We then measure what the lag is. So the first one was like 5 days, the second one was 7 days, the last one was 13 days. You then group them together. You apply that formula. So clearly 5 is the minimum, and then you calculate it. And that's one feature, right? So now imagine that you have like billions of these impressions, and typically what happens is for a modeling exercise, you have 100 to 200 features that needs to be calculated, right? So it's a very compute intensive exercise, and not only that, I think it takes a long programming time for you to come up with a list of features. We looked at that problem. For us, we were a software as a service company. We were not doing like multiple different kinds of modeling. We were actually doing 2 different kinds of model. One was market mix modeling, and the other one was attribution, right? We were not doing like lots of different kinds. But on the other hand, we were working with different data sets. So each customer, let's say Hilton comes in, we had to work with that data set. So the data sets were different on a per customer basis, but the modeling problem itself is the same. And the feature set depended on the data set that you would have a laundry list of 200, 300 features, but the feature set itself is dependent on the data set that you're trying to do. So we had to calculate all of these features as fast as possible, right? And so again, so this is something that what we said was the only way we could actually get there is to eliminate coding for all feature engineering. We said no coding. As soon as the data comes in, all of these features had to be calculated without a single line of code being written, right? And we've again similar to the previous thing, we've done fairly well. So what this chart shows is the number of hours different personas spent on a project. Strategist is kind of an analyst that goes to the customer and talks about talks about how the marketing is working. Data management is your data operations person. This is the person who's kind of running the queries and so on. Modeler is your modeler who's creating the models, and then finally you have ops support. When we started, it was entirely a manual exercise. These stacks were written. They were written in SAS code, written in laptops. We then moved on to again, on the cloud. We started using SQL. It brought down certain number of hours. We optimized the SQL. It did bring it down even further. But I think where we really started seeing that growth when we moved to this web scale kind of data where there are billions of impressions and you need to scale it is the next step where we were coming up with this this thing where we eliminated coding. This is going to be an eye chart, but I'll try and explain as much as possible. So the way we did it was we made sure that the entire pipeline, the back, was completely config driven. So as soon as a data set comes in, that data set is represented by a config. You see on the top corner, it talks about what are the dimensions and what are the facts and what are the metrics and so on and so forth. Everything is kind of specified by config. All of the code is in the bottom corner that you see. All of the code, we created our own Pidgin SQL, and we represented that code in a Pidgin SQL, right? And it had annotations to it on where the parameters need to get substituted. Then, when a new data set came in, what would happen is there would be two-step mapping. The first step that would happen is this code would be taken, and the parameters would get substituted with real parameters, right? And then we would take a target platform like Hive or Spark or something like that, and we would generate the code, right? And so for these 200 features, we would actually have one giant SQL file which would compute all of these features, and we would have like one big run which will do the stack generation, right? So it eliminated coding first of all. So it eliminated all the human aspects associated with the stack generation. The second thing it did eliminate was the performance, because here you are not trying to go and work on performance on individual SQL queries. You have a template, and therefore you have a predicted SQL signature, and then you are trying to optimize that SQL signature over a period of time. And not only that, if you wanted to move from, let's say, Hive to Spark, then I didn't have to worry about a large number of these SQL queries sitting all over the place. We had to go sit at these template libraries, and we had to make sure these template libraries are then generating Spark SQL instead of Hive SQL. And we've done that. We've kind of like we are predominantly a Hive shop, but we have tested it on Spark, and for most part it works, right? So these are like the two innovations that we did. One was on decision support system, another one on feature engineering, which helped us scale. Any thoughts on this, on the feature engineering itself, on what you guys have done?
I mean, for us, it's usually like depends on problem, and this is kind of great solution that, yeah, we didn't have anything that generic. My question is, do you guys treat numeric and categorical features different way for features engineering? And can you tell if it's not a big secret how, like, do you engineer different features and overlap between features, like combinations of them? And how many features, like, for example, if I give you 10 features, what's output of featured engineering features? Like, will it be 100 or 1,000?
So if you have, so let's go with it one at a time. So if you have 10 features, you're saying, if you select 10 features, right? The output for us, the stack is basically users, right? And then paired with activities for each users, and then the number of features, right? And it's a big table. So if you have 10 features, then it'll have 10 columns in the output, and then it'll be for every user and every activity, right? And I think I've got a friend in the audience who can correct it also. And then does that make sense, or is it?
Yeah. Like what we do, because like sometimes 10 is not enough to build something predictable, so we like manually like figure out like, okay, let's have some multiply column 1 to column 2.
Oh, yeah.
Or because
so all those expressions, like those become like in your input config.
Yeah.
So you can actually go and like literally write down your stack.
Yeah.
You can have your features.
Yeah.
And then you can have expressions of those features,
yeah.
right? The only thing is, so for example, has done before is a function, right?
Yeah.
The GHT is a function. So you cannot like arbitrarily come up with some function. You have to know the function before, but you can write expressions of the function, and you can have any number of features in your thing. And this is just an XML config that you have.
So you let user figure out what functions and features it do. If it's time variables, and you use lag for that impression TV examples.
Correct. You can actually go and specify whatever, like you have the input. Input of course is fixed, like the number of dimensions and the thing is fixed, and you can even there you can select what dimensions you want to look at.
Okay.
The stack, you define it in another XML file.
Okay.
And you go and specify the list of features that you have. And you can have expressions of that features also. Like you can say, like, for example, in your case, feature 1 into feature 2.
Yeah.
Or feature 1 into 10 or something.
Exactly.
Yeah, those expressions are also possible.
Yeah, that's kind of interesting, because if you ask about experience, like it's always like some small or big problem. We have to solve it quickly and then move on. Like, I mean, at least environment where I came from. And yeah.
So even in that case, my question is, let's say in that case, you have many people writing these different functions.
Yeah.
They might write the same function again and again and again. Even they're having like this template library, and then like using the template library to generate the code, as opposed to like just like like allowing people to write arbitrary SQL. Wouldn't that still be helpful?
It kind of depends on problem. For example, if you're solving churn problems, then it's one thing. If you solve in recommender system, then it's another thing. And if you just do high-level analytics and predict something on market, that's third thing. So it depends on problem, data, and it's not like we do it every time. And sometimes we don't need feature engineering, and that's why like there is like something like generic. And again, like a speed of how it's done and how solution needed to be taken, it's kind of different. So I wish we can like implement something like that, but it's sometimes faster like to build some model and move on, because it's another problem.
So the number of common features or number of common functions is not that much in your case. So you're saying like building this library doesn't it's just building it one-off is much better than building a library of these functions. Is that what you're saying?
Yeah, something like that.
Okay.
Yeah.
I was just wondering why you had like those different equations. Like, how did you arrive at those? Like the 1/1 plus x, like this GHD?
So these are all like, what happens is as people work on a particular domain, they find that this particular metric is a good feature for the model, right? These functions are all like, that particular metric was calculating the decay of how it influences an user to go and purchase.
So
right?
just a fit to the like curve fitting.
Correct. At the end of the day, you're trying to do that, but I think these are just like different, like when you're working on a domain, then you come up with a list of features that you're interested in, right? And then you create those metrics first, and then you then use those metrics to then go come up with the model and come up with the predictions. So the equation that you saw was one of the features that you come up with. How you come up with the feature is just understanding the domain. That's the whole data science aspect of it.
Okay.
Does that make sense, or was it?
Yeah, totally. Was that the same thing for it was like log of x plus 1?
Correct. So there are multiple aspects of it. I mean, one is actually the equation, the feature, the expression itself, and then how the equation is represented, right? Why would you want to represent it in the form of that equation? All of that is like the modeling aspects of it.
Okay.
All right. Thank you. Appreciate it.
Thank you.